Today we'll discuss the properties of logarithms. There's basically three. First one is if I have a log base of a product of two numbers, that's equivalent to the log base of one number plus the log base of another. So this is how you would split it apart, or if I had the sum, you could make it into a multiplication. We're going to be going back and forth today. If I have the log base of a division of two numbers, that's the log base of that numerator minus the log base of that denominator. And lastly, if I have the log base of a number to a power, I can take and bring that power out in front and thus multiply that exponent by the log base of the number. All right. So we're going to use these properties to combine and expand some expressions. So here's an expanded expression, and we want to write it as a single logarithm. Now we notice that this is a sum of two individual logarithms, so that's that first property that says if I have the sum, I can go to a product. So I have the log base A of 6 times 4, or the log base A of 24. In this case, you'll notice there's not only a subtraction, but an exponent. And just like in our order of operations, we want to do our multiplications first before we deal with the subtraction. So I'm going to take and bring this power, or this multiple, up to the exponent of that number. So I have the log base A of 4 cubed minus the log base A of 5. Now I can deal with this subtraction, changes it into a division. So this is the log base A of 4 cubed over 5, which, if I want to clean that up a little bit, 4 cubed is 64 over 5. Similarly, in this problem, there's that multiple. I have an addition, but in this case I have a regular number, and I want to express this as a single logarithm. So I want to have in the end log base 8 of a number. And what I'm going to have to do is change this number 2 into a log base 8 number. Alright, now I can do this in my head. You might have to think about it for a while, but log base 8 of what number equals 2? Alright, now I can write that another way. I can say log base 8 of what number equals 2, and we've solved these numbers before. We slide the base, get 8 squared is equal to x, so x equals 64. So I can rewrite this whole thing as 2 log base 8 of 3 plus log base 8 of 4 minus log base 8 of 64, because what power of 8 is 64? 2. Now we combine all this, go left to right once again, but deal with the multiplication first. So this is the log base 8 of 3 squared plus log base 8 of 4 minus the log base 8 of 64. Once again, left to right, log base 8 of 9, because that's 3 squared, times, because I have the addition, 4, divided by, because I have the subtraction, 64. Or log base 8 of 34 over 64, which simplifies into one log base number of the log base 8. 2 goes into both of these, of 17 over 32. And I've accomplished the task. So now we're going to go the other way, and we're going to split it apart. Now, in this case, what we need to do is we need to kind of go reverse order of operations. In other words, do our additions first and then do our powers last. So in this case, I see I have a multiplication which I can split apart into an addition by that first property. So I have the log base 7 of m to the 4th, and I'm going to add that to the log base 7 of w. Now notice I still have this exponent here, and it says use the properties of log to write an expression as the sum or difference of multiples of logarithms. So I can make a multiple out of this power. I have 4 log base 7 of m plus the log base 7 of w, and I'm done. Next, I want to use the properties of logarithms to write the expression again in a sum or difference of multiples of logs. This guy has a radical of index 3 and power, so I'm going to change this to an exponential. So I have the log base 4 of m to the 5th n squared, and all that is to the 1/3 power. Now I have a choice. I can multiply this in, or I can bring it out in front since it's an overriding power right off the bat. And it really doesn't matter. I'll just go power of a power right now. So I have the log base 4 of m to the 5/3 n to the 2/3. And then you'll notice I have this multiplication here, which I can split apart into an addition. Log base 4 of m to the 5/3 plus log base 4 of n to the 2/3, and then bring my exponents out in front, so that's 5/3 times the log base 4 of m plus 2/3 times the log base 4 of n. So this problem is actually a little bit trickier. We're still going to pull it apart, but you'll notice it's pretty easy to see I have a division, I have these powers, but what a lot of people forget is there's a multiplication of the 1,000 and the m to the 7th. So we're going to have to deal with all that. So I have the log of 1,000 m to the 7th minus the log of n cubed. Notice there's that multiplication. I'm going to pull that apart right now. So I have the log of 1,000 plus the log of m to the 7th minus the log of n cubed. Now here's an interesting little tidbit. We don't see a base on this, but there is a base. If I ever see regular log written, that's equivalent to the log base 10. We call this the common logarithm. So if I wanted to rewrite this, I could, and I will just so you guys can get used to it. It's the log base 10 of 1,000 plus the log base 10 of m to the 7th minus the log base 10 of n cubed. This will probably be the only time I write log base 10, just because it's implied that if there's no log base written, it's a log base 10. Just like in our square root, the implied index is 2. So you'll notice in this case, very easy to see I bring these powers out, but what power of 10 is 1,000? Well, 1,000 is 10 to the 3rd, so the log base 10 of 1,000 is actually just 3 plus 7 log base 10 of m minus 3 log base 10 of n, and then we're done. So this is another way of doing the same type of problem, but they're asking us to express an answer not as an expanded form, but in terms of these quantities c and d. They tell us that c is equal to the log base 3 of 10 and d is equal to the log base 3 of 5. So we're going to use these expressions, split them apart to try to get log base 3 of 10s and log base 3 of 5s, and every time I see those, substitute c or d in. So we see here that 50 just happens to be 5 times 10, and I can split this product apart into an addition. So I have the log base 3 of 5 plus the log base 3 of 10. Given that, log base 3 of 5 is d. I can make that substitution, and the log base 3 of 10 is d. So this is just d plus c. In the case of 250, I have to figure out what numbers multiply to 250. Well, and not only that, because it's pretty easy, I can use the log base 3 of 2 and the log base 3 of 125. But the problem is that's not in 3s and 10s, so I want to use those. So it's pretty easy to see 250 is 25 times 10, which is the log base 3. I like going powers, so I say 5 squared times 10. And then I'll split that apart. So I have the log base 3 of 5 squared plus the log base 3 of 10. Then I'll bring that exponent out in front. So this is 2 log base 3 of 5 plus the log base 3 of 10. And now I'm ready to go substitution. Log base 3 of 5 is d, so that's 2d. Log base 3 of 10 is c, so I have 2d plus c. And lastly, we go to log base 3 of 270, and I want to try once again to do 10s and 5s, but I'm going to have a problem here because I got a 27 in this. I see that if I go the log base 3 of 27 times 10, that's the first thing I can think of when I go to 270. And if I split that apart, that's the log base 3 of 27 plus the log base 3 of 10. There's no way to get 5s or 10s in 27. Fortunately, though, I noticed that 27 and 3 are related in terms of bases. And since the log means what power of the base is the number, I can say what power of 3 is 27. Well, that's 3, and that's the answer. Log base 3 of 10 is just c, so it's just 3 plus c is my answer. And that's all we've got. Make sure you do your Connect Ed and fill out your survey. We'll talk tomorrow.